Okay, so welcome. Today we will discuss the last chapter of our inorganic chemistry for section 13 and 14. The leftover chapter was the redox chemistry. Today we will discuss the redox chemistry, and you all know this is a very special type of reactions. It involves oxidation and reduction, and you know probably that how the oxidation comes. The term is basically the oxidation of the metals and oxygenation of the metals to metal oxides, and the reverse reaction, that is the reduction. And this is very important in living systems. As example, in biology, many biological reactions involve the electron transfer reaction. This is nothing but redox reaction. We will discuss the principles of the redox chemistry and some few concepts on the redox chemistry. So, let us start. You know that in biological systems, in your 10+2 biological studies, that many systems are involved electron transfer. One of the system you know from the childhood, that is the respiration, that is the oxidation of glucose that is so basically the oxidation of carbon to carbon dioxide and reduction of water oxygen to water. So, this is you know from your childhood. So, this is one example of redox reaction. Like this, lots of important redox systems in biology. As example, NADP plus to NADPH, many metalloproteins, especially the iron sulfates, also involve the redox chemistry. And these are the few redox couples. We will discuss more what is the redox couple later, but these are the some list which are involved in biological systems. As example, you see from here, it's is all these redox couples are basically involved in biological system. We will not discuss much in the biology. We will discuss the concept of the redox chemistry in this class. This is many of you know already in your 10+2, that is the extraction of elements from its respective ores. All these are involved, most of the extraction process are involved redox reactions, either oxidation or reduction. As example, the chlorides, the halides are oxidized to its elemental form by oxygen, and then oxides are hydrogenated or reduced to its respective elemental form, and many cases the coal is used as a reducing agent. So, all are basically you see the redox reaction. So, metal extraction is nothing but the application of the redox principle. And in environment, you know the rust is nothing but the oxidation of iron, and all of you know what is the rust, is basically the +3 oxidation state iron oxide. So, before going to the main part of the redox chemistry, I will try to give some few concept of the redox reaction. As example, this one is very simple system where your copper 2 plus and your magnesium, and you see here this reaction. This copper 2 plus has become the elemental copper, and magnesium has become the dication Mg2 plus. Now, here you see this is the reduction by 2 electrons. So, plus 2 electrons is, and this case magnesium is becoming magnesium 2 plus. So, this is minus 2 electrons. So, this is a simple system, is a symmetric system, 2 electron addition, 2 electron plus 2 electron minus 2 electrons, but not necessarily that it will be a symmetric redox reaction. There may be involved 1 and 2 plus, and accordingly you have to balance how many metal atoms or cations are there. So, this is a reduction because addition of 2 electron, and this is a oxidation. So, I am so is subtraction of 2 electrons. Now, all the redox reactions are basically the basically the constitution of two half reactions. One is the oxidation and one is the reduction. So, this is a one half cell reaction, this is called, and this is another half reaction. So, this you will see that all the redox reactions involved two half reactions always, one is the oxidation and one is the reduction. So, this in this case this is a reduction, and this case this is oxidation. Okay. So, we will come again with this concept, what is the reduction potential, after few slides. So, this before going to the reduction definition of the reduction potential, I will just come to the very interesting you can say applications, that is the balancing the redox equations, and these probably most of you are familiar. So, I will just touch this concept by the concept of the redox reaction, how many electrons are adding and how many electrons is coming out, you can balance your redox reactions. This is a very simple system, like you will see that Fe2 plus you have probably read in your 10+2, or probably you might have done this redox titration, is a very well known and famous redox reaction. So, Fe2 plus is becoming Fe3 plus here, and you would see MnO4 minus is becoming Mn2 plus. Okay. So, for this one, what you have to do first, you have to see you have to first identify the two half reactions, okay, half cell reactions. So, one is like this one, Fe2 plus to Fe3 plus, and you find out the oxidation state first, that is the, so first step is the find out the respective cell reaction, half cell reaction, and then find out the oxidation state of the each side of that particular half cell reaction. So, here oxidation number is 2 and here oxidation number is 3. So, you will see here this involved 1 electron oxidation, and this one you will see this is plus 7 oxidation state number, and here it is 2. So, this is a addition of 5 electron. So, here this one, as I told 3-4 slides back, that not necessarily that number of electrons for each cell reactions, not necessarily that will be equal. So, you have to this is a example of a non-symmetric redox reaction, but ultimately you will see that this 5 electron and this is a 1 electron. So, to balance the equation, so what you have to do, you have to first multiply this 5 Fe2 plus into 5, this is then it will become 5 and this one will be 5. So, now you will see here what will happen. So, 5 Fe2 plus, then MnO4 minus, and so it will become the 5 Fe3 plus and Mn2 plus. Okay. Now, if this reaction is in acidic reaction, acid medium, so you have to accordingly you have to add the hydrogen. So, as example here you see the 4 oxygen. So, there will be 4 H2O, okay, and accordingly there will be, so this is you see 8 hydrogen atoms. So, you have to add 8 H plus, very simple. So, the first step is find out the respective half cell reaction, then the find out the oxidation state number, then see how many electrons are involved in each half cell reaction, and then the balance the number of electrons, oxidation and reduction, that should be equal electrons, and if it is in acidic medium, you have to add the required number of protons, and the number of oxygen atoms will become the equal number of water molecules. and if it is a basic medium, then you have to add OH minus accordingly. So, very simple reactions. Okay. So, the few concepts as example, one is the Nernst equation. So, this is suppose is a very general way of writing. So, this is a ox, this is red. So, this is becoming the red 1 and this is becoming OX2. Now, this you know the Nernst equation. So, this is a standard reduction potential, okay, and this is the reduction potential at the particular condition, and this will be related to E is equal to E0 minus RT by NF ln Q, and Q is the quotient. This is the this is basically the concentration of the species at right side by the concentration of the species at the left side. Okay. So, this is called the famous Nernst equation, and these are all well known constants. Okay. R is gas constant, and F is Faraday constant, is equal to around 9500, and N is the number of electrons involved in the particular redox reaction. Now, you should have a very clear idea about the redox potential. Okay. We use this redox potential. Now, you have to understand the redox potential may be two types. One is reduction potential and one is oxidation potential. Do not be confused with these two terms. One is the reduction, one is the oxidation potential. By convention, we always use reduction potential. So, if I give a potential of a particular redox couple, we actually mention the reduction potential, and very strictly whenever as example, suppose this is my metal and this is my N plus the metal cation, and I am giving like say one electron, and it is becoming it is being reduced, and it will become N minus 1. So, this is a reduction reaction, and if I tell that the reduction potential of this couple we generally represent as like this one, like this one, okay, say x volt or millivolt, anything. Okay. So, millivolt or volt we represent generally as a volt. So, if we say that reduction potential of this couple Mn plus Mn minus, the corresponding reaction, redox reaction is half cell reaction is basically this one. Okay. So, not the reverse one. Okay. So, not the, because this is basically the oxidation potential. So, its value will be same, but the sign will be opposite. Okay. So, if we say that reduction potential, we tell that the reduction potential of a particular cell is this reaction. Okay. So, and E0 is at a standard condition, and E is that and a particular condition. Now, we have to say for an unknown couple, okay, redox couple, we have to say we need to calculate the E. Now, how we will calculate? Okay. So, for that what we have done, we have taken a particular half cell reaction as a 0 volt, not necessarily that it is actually 0, it is it has been considered as the 0 volt. Okay. But this absolute potential is around 4.4 volt of this couple. Okay. But we have by convention we have considered that it is 0 volt, and with respect to this hydrogen electrode, standard hydrogen electrode, we have measured all the redox couples. We basically represent for all the redox couples with respect to the hydrogen half cell reaction, that is actually this one. So, this is a again you see this is a 0 volt. So, this is this called standard hydrogen electrode, and you see this is basically 1 bar hydrogen pressure, and this is a platinized platinum electrode. This is a standard condition, and H2O plus that is in 1 molar. So, 1 molar acid solution. Okay. So, this is just a convention. There is a lot of other standard electrodes, as example calomels. Okay. I mean that is but hydrogen electrode is more popular and very easy to construct. Okay. So, most of the discussion and the slides I will show all the potentials are basically with respect to the hydrogen electrode. So, as example this is a table, you no need to remember all this data, but I just want to give a few conceptual points here. As example, here you see that hydrogen is this one. Okay. So, this is a 0 volt, as I told, it is considered, and these are, you see here all the all the redox couples here. As example, here you see the fluorine fluoride, this is 2.87. Okay. And here you will see Na plus sodium, okay, and it is sodium metal minus 2.71. So, qualitatively what is the physical significance of this value? Okay, the 2.87, 1.78 higher value, quite higher with respect to the standard hydrogen electrode, and here you see these are quite low value in negative. Okay. So, what is the significance? So, this is being see the higher that these are all reduction potential, standard reduction potential you see here. Okay. You will get this table in any standard textbook. Okay. You no need to remember all these things. Okay. But just try to understand the concept. So, here you will see the more reduction potential means it is a stronger oxidizing agent. That means it will oxidize to any other redox couples species with the low reduction potential. As example, this one, this couple will very happily can reduce, say, the silver we oxidize the silver, this one. Okay. So, as example, like here you see that Fe3 plus Fe2 plus you take 0.77 volt. Okay. And you take the like nickel 2 plus Ni this couple. So, if this one, the Fe3 plus Fe2 plus, this couple will oxidize easily the nickel 2. So, by this table you can judge that which couple will oxidize to which couple. Okay. So, this is, so that means if more reduction potential is the more oxidizing agent and low reduction potential is the stronger reducing agent. So, that is the whole concept of this table, and all this E value, as I told, E0 is with respect to its hydrogen electrode. Okay. And many many reviews or many textbook you may see that this potential value are also tabulated with a reference of other electrode, as example calomel electrode, or with respect to the ferrocene. So, you have to be little careful about this data. Okay. But for our discussion we will consider the standard hydrogen electrode. So, no need to be worried here. Okay. The few important redox reactions. So, it is good to understand before going to another important section, that is the Frost diagram here. Disproportionation reactions. You know that hydrogen peroxide is a very interesting molecule, interesting species. It can spontaneously give the water and oxygen, and you know that little bit acid like sulfuric acid, it acts as a negative catalyst. So, it basically stops this disproportional reaction that you know from your 10+2. So, you see here this hydrogen peroxide is spontaneously from the water and also the oxygen, and here see the oxidation state at the central metal atom. Here you sorry, the central atom here is a -1 and it is 0 and it is -2. So, here you see that one single species is converting spontaneously to two other species with a different oxidation state. So, this is called disproportionation reaction. So, is one -1 to 0, -1 to -2. So, one is oxidation and one is the reduction. So, one single species undergoing oxidation and reduction to give the two other species. So, many such examples are known. Okay, this is just one example, and this I will come later. This is you can predict it whether it is spontaneous or not, and this very simple equation that you know this one in P0. Okay, so this we can calculate very easily with if we know n is the number of electrons involved, is the potential. So, we can if we can see that if for a particular redox reaction this delta G0 is negative, then the reaction is spontaneous. Okay. So, this you can consider as a home assignment, okay, and check that whether this disproportional reaction is spontaneous or not, just you can quantify it. So, please whenever you please do it yourself as assignment. Okay. So, there are a lot of examples. This is like another example. Okay. This copper plus, you know, it is not stable, it's in aqueous solution, it spontaneously forms copper 2 plus and elemental copper. This is the reverse reaction, that is the comproportionation reactions. Okay. So, here just a reverse reaction, here you see that two species of the same element with different oxidation state is giving to a single species, and both, and here you will see the oxidation state are different. So, two species are converting to a single species of the same one oxidation state. This is called the comproportionation reaction. So, exactly opposite of the disproportionation reaction. So, these are a typical special example of a redox reactions. Okay, and this is anyway we will discuss more in the Frost diagram. So, as I told that you can calculate your this whether this reaction is spontaneous or not by simply this famous thermodynamical equation. So, delta G0 is equal to minus NF del E0. If del G0 is negative, then the reaction is spontaneous, and if is positive, then the reaction is not spontaneous. Okay. So, like here this one simple example. So, here you see that the H plus H couple. Okay. So, this is, as I told, if I write this couple, you have to write like this one H plus H. Okay. And if you write this couple, you have to write like Zn 2 plus and Zn, and these are reduction potential. Okay. So, and if it is standard condition, so you should write like this one. Okay. So, you will see here this is 0 and Zn 2 plus 2 electrons. Okay. So, this is minus 0.76. Okay. And so, if you just do the A minus B subtraction, so 2H plus Zn 2 plus H2, and as I have just reversed the minus this one. So, it will, this minus value will become plus value, and you put it here NF delta E0, you will, as it is positive. So, delta G will be negative because this is a minus sign. So, that means that this reaction is favorable, reversible and spontaneous. So, you can very simple, so far what we have done, we have learned that what is the redox chemistry, redox reaction, what type, and what is the reduction potential and what is the physical significance to be a higher reduction potential and the lower reduction potential, and who will be the stronger oxidizing agent, who will be stronger reducing agent. And then we have discussed how you can judge that whether this will be the reaction will be spontaneous or not, and the special type of redox reaction, that is the disproportionation reaction and the comproportionation reactions, okay, and the Nernst equation. So, probably you have heard the Latimer diagram. This Latimer diagram is nothing but to make is very difficult to remember all the particular redox couples individually. As example, with of the same element like Mn2 manganese, you know that manganese can exist in a different oxidation state, Mn2 plus, Mn3 plus, Mn5 plus 5 oxidation plus 7 oxidation. So, it is very difficult to remember all the redox reactions and its respective reduction potential individually. So, to make it more simplified, to make it more organized, the few diagrams have been developed time to time. One is the Latimer diagram, that probably you know this one. This is a very simple representation. Here you will see. So, Latimer diagram is represented as a horizontal line. So, as example, if it is like x, suppose x 5 plus, then x 4 plus, then x 3 plus and x 2 plus, like that. Okay. So, like that. So, it is basically the for a particular species, the highest oxidation state will be the left and the lowest oxidation state will be the right, and here you will see some digit. Okay. So, as example 1.5, 1.0, like that. This is nothing but this is a volt. In convention, we do not write volt here. If it is not written anything, you have to consider this is a volt. Okay. So, this is a very easy way of representing a particular series of redox species or redox reaction of a same element. So, this is called Latimer diagram. But this is simple, but you will not get lot of information from the Latimer diagram. Okay, we will come to this discussion, and that is why the another diagram has been developed, that is the Frost diagram, that is very useful, and this is represented as a graph. So, this one is a 2-dimensional representation. So, here you will see the oxidation state, and here it is the N E0, and you know that delta G is equal to minus N F E0. So, this is basically you will see this is almost parallel to the delta G 0. So, this y axis is basically a parameter parallel to the delta G 0, and this the x axis is the oxidation state, and you will get if you construct the Frost diagram from a Latimer diagram, you will get like this one. Okay, we will come to the real example, and you from this kind of diagram you can know lot of things. Okay, I mean lot of information you will get from a Frost diagram, and that is why it is very popular. And so, this is basically what we are plotting. We are plotting the delta G 0, okay, with respect to the number of electrons or the oxidation state of the particular species. Okay. So, more so if you say this a particular species you have a low Ne0, that means it is more stable, like that. We will come to a real example, you will understand there more clearly. So, as I told that this is represented as a horizontal line, like so, one dimensional, and this is very easy to represent, but with limited information. Okay. So, this is one typical example of Latimer diagram of chlorine in acidic solution. So, as you know, this is +7 oxidation state ClO minus perchlorate, and here you will see ClO3 minus, HClO2, HClO, and this is the 0 oxidation state Cl2 and the last chloride. So, this, as I told, that this is all in a volt. So, no need to by convention you no need to write the unit of volt, it is considered to be as a volt. So, you see 1.2, 1.18, 1.65, 1.63, 1.36. This is no need to remember, okay, but you should understand the significance. So, you this one you will see that +7 to +5, okay, the oxidation state. This one you will see that +1 to 0, okay, and this, if you have this information, okay, and if you know that how many electrons are transforming from here to here, okay, you will be able to know the respective reduction potential of a like other couple, like this one or like this one. So, what you have to measure the respective delta G0, okay, and this is by this one, and then you can stepwise you calculate, and you will be knowing the non-adjacent electron the reduction potential of a non-adjacent species. Okay. So, for adjacent species it is already there. So, this is as example, you know that HClO to Cl minus. Okay. So, you have to calculate for this one, and then the delta G0, and then you from there you calculate the your NFE0, and you know that how many electrons are involved. So, from there you will get the E0. Okay. So, this is easy, very useful. Okay. As example, like here you see here, suppose I want to calculate this the E0 of this couple non-adjacent. So, this one you first balance the equation, and you see that how many electrons are involved. Okay. So, what you have to do first, you have to first see that what is the oxidation state of the central atom, like the chlorine, where the oxidation state are changing for which atom. So, this is +1, this is 0, this is -1, okay. And then you calculate the delta G. So, the equation like for this one, for this one, and like for this one and this one, and then you add it, and you will get the delta 0 of this one, and from there you will get the E0 of this. It is very easy, it is nothing but just doing a simple arithmetic. Okay. So, here so by Latimer diagram, that is why it's nice, you can calculate your the electron the reduction potential of a non-adjacent species. If you have the Latimer diagram, you will be knowing that which one is the strongest oxidizing agent, which one is the strongest reducing agent from the Latimer diagram. But you will not have a you can calculate that what are the disproportionation couples, what are the comproportional couples, but it is not instant. So, you have to calculate, and then you have to judge it. Okay. So, that is fine, but it is little time consuming. Okay. But I will show the another one, okay, that is the first diagram. So, that is very easy, little different from the Latimer diagram, but conceptually, as I told, is very similar. This proportion reaction I will come later for the first diagram, because anyway you have to discuss there again. So, here as I told that this is a representation of the different species of the same element. So, species means with different oxidation states, redox species. So, here is the oxidation state or is the number of electrons associated with, and this is basically the redox Ne0, Ne0. So, this is parallel to, as I told, that this is your delta G0 thermodynamic parameter, and this is y axis, this is x axis, and this one I will come with a example. Like you see this Latimer diagram, this is the nitrogen Latimer diagram in acidic medium. So, if I give a Latimer diagram and if I tell that okay, you construct the Frost diagram, what will be your first step? So, first step is look at the Latimer diagram carefully and assign the oxidation states of the main atom, okay, where in a main atom means where your oxidation on which the oxidation states are changing. So, like here NO3 minus. So, you see the oxidation state for on nitrogen is +5, N2O4 +4, here it is +3, +2, +1, this is 0, this is -1, -2 and -3, formal oxidation state -3. Second, you have to now see that which is the species with 0 oxidation state. So, this is for nitrogen, this is the 0 oxidation state. So, that is the this one. Now, this is important, that is why I am highlighting, because all the Frost diagram you have to calculate, you have to construct with relative to the oxidation state 0. So, that is why this is important. Now, what you have to do, you have to calculate the respective E0 value, okay, with the respective E0 value with respect to your 0 oxidation state species. This one, and from the Latimer diagram we know how to calculate the E0 from a non-adjacent species of the same metal, okay, of the same element, not metal, it may be anything. So, you calculate the E0 of with the couple NO3 minus N2, N2O4 N2, HNO2 to N2, NO2 N2, N2 N2, then this one to this one, this one to this one, this one to this one. Okay. So, these you have to construct, you have to calculate. Okay. So, like here, okay, you have seen it. So, this is this you have to calculate, okay, like this one. So, once you calculate all this value, okay, by stepwise calculating the using this equation, okay, and then you will be able to by very simplified, okay, you can just use this equation. So, it is please practice it, it is very easy, okay, nothing, is a simple arithmetic. You have to be just careful of the oxidation state and the number of electrons associated with this one, that is you have to careful. So, if you like do this one, okay, from NO3 minus to N2, okay, so you will be able, you will get the E0 1.25, okay, and for N2O4 to N2 you will get 1.36. Please do it today itself, okay, and recheck it, okay, it is very easy, you will get this value. So, once you calculate the E0, okay, and as I told that the y axis is simple Ne0. So, you have to multiply with oxidation state, okay. So, your then y the is ready, the point y is ready, and x is nothing but your, so this is y, this is x, and X is basically your oxidation state number. So, once these are ready, you will see that for nitrate you will get 1.25 for NO. So, this is 2 into 1.68, here 5 into 1.25 into 5. So, all you are getting these points, and then just simply you plot as X and Y, and you will get a plot like that. This is acidic medium, and you see here, see carefully what is the significance. Okay. So, what information we will get from this diagram. Okay. It is very important. So, here you see this is a first diagram of the nitrogen in acidic medium. So, you see carefully. So, this is ammonium NH4 plus, this is nitrogen, and this is HNO3, and here very interesting, here you see that this is the species with 0 oxidation state, and this is the species with -3 oxidation state. Now, as I told that Ne0 is basically parallel to delta G0. So, is less delta G0 is basically the stable species, and that is why for nitrogen the NH4 plus is the most stable species, and that is why it is at the lower. So, lower, if you see any species at the lowest delta Ne0, so that means in that particular series it will be the stable. And next is the nitrogen, okay, N2. So, you will get lot of information, okay, and also you will get this is the same thing, but in a base medium, basic solution. Okay. So, again you can calculate easily, very easily. So, you from like this is the first diagram. So, you have to calculate with respect to the nitrogen, and then you do the. So, this is a acidic medium and the previous one, and this is the basic medium. You will see the nitrogen is the most stable form, but in basic medium, in acidic medium NH4 is relatively the stable form, but in basic medium nitrogen is the stable form. Okay. So, now as I told that let us try to extract what are the information we will get from the first diagram. That is the most, I mean the ultimate goal of constructing the first diagram. So, what you will get the information. So, first information you will get will know just by look at the first diagram. Okay, no need to calculate, just from the see the diagram you will be able to know that which species are the most stable. So, that means which oxidation state is the most stable state of a particular series. So, as example here in acidic medium, that has to be you have to be careful. In acidic medium, this one, that is a -3 NH4 plus is the stable form. So, then you can know the particular, calculate the Ne0 by simple calculating the E0 of that particular redox reaction of a adjacent species, just by calculating the slope of this by joining of the two lines. So, suppose I want to calculate the E0 of these two of the redox reaction of these two redox couples. So, simple, from the first diagram I will calculate the slope, okay, very easy. So, this one, sorry. So, we can calculate this one and we will calculate this one. So, you will from here you will get this, and the slope will be n E0 minus n 2 E0, okay, and by n1 minus n2. So, from the slope we will be able to know the E0 of a particular the redox reaction of two couples. So, it is very easy to calculate. Okay. No need to do a full calculation a delta G 0 and then adding it up. Okay. So, it is very simple and it will save time. Now, again you will be able to know that which one is the oxidizing agent, which one is the reducing agent. Like more positive slope is if you see that if it is more positive slope, then it is a good oxidizing agent. If it is less positive, then it is a good reducing agent from a Frost diagram. So, this is this is like this one you will see, like the potential at HNO2 is reduced to NO. So, this is you can very easily know that which one can particular species will reduce and to other adjacent species, or which one can a particular species will oxidize to other adjacent species. Now, I will tell that the disproportionation and comproportionation reactions. This is again is very interesting, as I told, is a very special type of redox reactions, and we have understood from the Latimer diagram that if the disproportional reactions where you will be getting two species of different oxidation state from one oxidation state species by particular element. Now, here you will be from the Frost diagram, you will be able to know that which species can undergo disproportional reactions without calculating the delta G 0. Okay. So, like in Latimer diagram, you have to calculate delta G 0 and you have to prove that yes, that these couples can undergo, this species can undergo disproportional reactions by. But if you have a Frost diagram in your hand, you will be able to know that which one can easily undergo the disproportional reactions. Okay. Like here, simple, in a Frost diagram, if you see the three species and like this one, this species and this species, if you draw a line and if you see that any other species does exist above the line, then this is unstable with respect to disproportionation reactions. So, this one will go the disproportional reaction to this species and this species. Okay. So, similarly, if you see, if you have a three species and you draw a line between these two species, and if you see that any other species does exist below the joining line, then this one is this species and this species is unstable to comproportional reaction. So, it is very easy. Okay. Just by look at the if you know that what is the concept of a Frost diagram, you will be able to know that which species can undergo comproportionation, which couple of species will undergo comproportionation reaction and which species can undergo disproportional reactions. So, as example, this is, you see that let us see, the red one is the acidic medium and the blue one is the basic medium. So, if I tell okay, you find out which one can undergo the disproportional reactions, okay, here in like acidic medium. Okay. So, here you see that this is, I am just drawing line here and you will see this is the above. So, this one in NH4. So, this one you will see that this is unstable with respect to disproportional reactions. Okay. And also like this one N2O. Okay. You will see this one also. Okay. Now, similarly, if you find out, if you see the basic medium, this one you will see this one is this will undergo disproportion to N2O, NO2 minus, and here you will see if I draw the line, with this one. So, this one and this one is unstable to comp proportional reaction, and it will convert to the NO2 minus. So, it is very easy, okay, like here also you will see. Okay. So, this one will undergo the comp proportional reactions. So, very interesting Frost diagram, okay, is very easy way to represent the redox reactions, and I have already I will send few assignments and also the summary of the slides to and you will see there are lot of assignments, lot of problems, small problems, very interesting. Please solve yourself, try to discuss, you can discuss yourself. You cannot do any group discussion, that is unfortunate, but try to solve yourself, read book, cyber whatever we have discussed, I have discussed fully from the Cyber Atkins inorganic chemistry book. This is very interesting, as I told. There are a lot of examples I will send as assignment and also the summary of the slides. And so, what I just want to mention few things, that one is please follow my ERP emails. I will give few assignments and the model question answers for tutorial classes, because tutorial class will probably it may be difficult to conduct, but I will give lot of assignments. Please check your emails, and if you have any kind of questions, any clarification doubt, please email me, or you can send your clarification in questions through my WhatsApp number. I have already emailed today. So, take care, and yeah, please be prepared for NSEM for inorganic chemistry. Thank you, take care, best wishes.